Okay, this video is for section 3.3, and you may be wondering if we're skipping 3.2, and the answer is yes. We'll come back to that later. So for today, we're going to talk about some specific information you can get from the first derivative. Now, in the last class, we already talked about critical numbers, so hopefully you already remember that critical numbers are when the derivative equals 0 or undefined. Okay. Now, something that we've alluded to before, but we're actually going to kind of make it be officially a part of the notes right now, is the function is increasing when the derivative is positive, and a function is decreasing when the derivative is negative. Hopefully that makes sense, right? Because the derivative is the slope. And so if the slope is positive, like if you have a line that has a positive slope, is it increasing? If you have a line that has a negative slope, it's decreasing. Now we're talking about any kind of a curve. So if I have a curve that does something like this, this curve is increasing in this first section. So all along here, we know the slope is positive. We've talked about how at this maximum point, we have a slope of 0. All along over here, we have a slope that's negative. Down here at this point, we have a slope of 0. And then the slope is positive again. Well, that's all this number 2 and 3 are saying. Okay. Now, in the last section, 3.1, we talked about absolute extrema. And we talked about how absolute can occur at critical numbers or endpoints. Well, now we're going to talk about relative extrema. And remember, relative extrema are those hills and valleys. These max and mins that are within, but like if this curve were to keep going all the way up here, so maybe this red one would be the absolute max, but we could say that this green one is a relative max. So for relative extrema, I'm just going to put here kind of in quotes. These are like, it's not just me using this phrase, textbooks say this as well. These are the hills and valleys. So it's not necessarily the highest point or the lowest point, although it could be. Okay, so relative maximum values occur when the derivative changes from positive to negative, which makes sense. If you look at this picture that I have up above, over here you've got the derivative is positive, and then it changes to negative, and at that point right where it changes, we know that we have a relative max. And similarly then I could say that a relative min occurs when the derivative changes from negative to positive. Now, if we wanted to get more specific, we could say that these relative max and relative min, they only occur at critical numbers. Only occur at critical numbers. And the reason I'm making a point about this is because that's in contrast to the absolute max and min, which could occur at the critical numbers and the endpoints. Okay, so guidelines for finding relative extrema. Remember, we did the guidelines last time for finding absolute. We said you find the critical numbers, and then you plug the critical numbers and the endpoints back into the original function. Okay, for relative extrema, you don't go back to the original function. For relative extrema, you stick with the first derivative. So number one, use the first derivative to find the critical numbers. This is the only step, well, if my pen would write, this is the only step that is the same as what we did on absolute max and min. Okay, so once we find our critical numbers, we're going to make a number line. To represent the x-axis, and this is important, of the derivative, okay? So you want to be sure and label that number line as the derivative. And so what we're going to do is we're going to analyze the derivative and decide whether or not the derivative is positive or negative. So we'll label the intervals on the number line as positive or negative, meaning is the derivative in that interval positive or is the derivative in that interval negative? And then once we know how the derivative behaves, positive to negative, negative to positive, we can label the intervals as increasing or decreasing. And then we can also identify the relative extrema. Okay, so here's how it works. And this little box at the top is just kind of a little synopsis summary since this is a separate page. So find all intervals on which the function is increasing, decreasing, identify relative extrema. So I know I'm going to look at the first derivative. So I'm going to say that the first derivative is, if I bring down the 5, I'm going to have x to the 4th. Bring down the 4, I'm going to have 3x cubed. Bring down the 3, I'm going to have 2x squared. Okay, so there's my derivative. If I want to find the critical numbers, I want to set this equal to 0. And so I think I'll factor out an x squared. Right, see if I can keep factoring, trying to find the zeros. So I think x minus 2, x minus 1. Okay, so I know I have critical numbers at x equals 0, x equals 2, and x equals 1. Okay, that we did, excuse me, the other day. So now what we're going to do pertaining to the critical numbers is right here at this step, we're going to create a number line and label it as the derivative. So this is a derivative number line, and it kind of represents the x-axis. I mean, we could draw the x and the y, but I don't want this to be about the graph of the derivative, although sometimes we'll think about the graph. Put on your critical numbers. So I have 0, 1, and 2. Okay, so one way to analyze the derivative is to use end behavior, and this is where end behavior is going to become a big deal. So if you have been avoiding it because you forgot, then you need to get familiar with it quick. So when I look at this derivative, it's a 4th degree, right? The overall the overall derivative is a 4th degree. That means I know that the ends, both ends, are going up because it's a positive out in front. So both ends are going up. And then when you look at the individual factors, that tells you if your curve bounces or if it passes through that particular critical number. So the x equals 0 came from the x squared. Notice it's an even exponent, so that means I bounce off. And then the x equals 1 came from this factor. Notice it's an odd exponent on the factor. It's an exponent of 1. So that means when my curve comes back through, it's going to pass through 1. And then the x equals 2 critical number came from this factor. Notice it's an odd exponent on that factor, so that means the curve passes through at 2. So that is a very rough sketch of the first derivative, but what I care about from that is because the graph is above the x-axis, that means the derivative is positive. In the next interval from 0 to 1, the graph stays above, so the derivative is positive. From 1 to 2, the graph goes below, so this graph is negative. And then from 2 on out, this graph is above, so this graph is positive. And remember, this represents the derivative. So in fact, I think what I'll do is I'm just going to get rid of this graph, because otherwise you're going to get yourself confused with increasing, decreasing. All we want to know is the first derivative positive or negative? And we've labeled that. So now, based on the information that we mentioned before, because I know that the derivative is positive, that means that the original function is increasing in that first interval from up until I get to 0. Then the original function stays increasing, and then the original function is decreasing, and then the original function turns back to increasing because of how the derivative changed. So that's kind of a nice way for us to look at it and organize it. As far as AP exam, what I have right here in this box is a great thing for us to look at, but the people who are grading your AP exam won't read that, okay? Because that's a chart. They don't read charts. You have to interpret the chart for them. So if this question said, find all intervals where the function's increasing and decreasing, we would have to say f is increasing on the intervals, I'm going to say negative infinity to 1, and it is okay to go ahead and put both of those intervals together, and the interval from 2 on out to infinity. And we could say f is decreasing on the interval from 1 to 2. Notice how I used the word on and not at, because if I had said f is decreasing at this 1, 2, it would imply that that's an ordered pair, like the function is decreasing at that ordered pair. So the word on means you're talking about an interval. Okay, but that's not all the question asked. It also said identify all relative extrema, meaning relative max and relative min. So when you look at this chart here we have of the derivative, do you see that right here at x equals 1, the derivative changes from positive to negative? So think about it. If my original function is going from increasing to decreasing, hopefully it makes sense that the original function is going to have a relative max. So I'm going to say relative max at x equals 1. Now, if this were the AP exam, you would have to go on to say because derivative changes from positive to negative. And we can say, notice the derivative right here at 2 changing from negative to positive, so relative min, and this is implying f has a relative max and f has a relative min at x equals 2 because derivative changes negative to positive. Notice something that's going to become a big deal when you're presenting your answers, on a test or on the AP exam, is notice I've labeled each function. It was f that had the relative max, it was f that had the relative min, but it was the derivative that changed sign. It was the derivative that changed sign. Okay? So look at number 2. Everybody loves a good trig question, right? I'm just going to kind of make this a little bit smaller so it's not impeding on my question. All right, so determine the intervals on which the function is increasing, decreasing, identify the relative extrema, but this time it's a trig function. Okay, so first we find our critical numbers, which come from the derivative. So the derivative is, we have to do a product rule, right? Sine times cosine. So derivative of the first is cosine times the second. Well, if I'm going to multiply by cosine, I'm just going to call that cosine squared, plus sine, and then the derivative of cosine is negative sine. So what I have here is cosine squared minus sine squared. Okay, critical numbers. I want to set this equal to 0. And then I want to solve for x. Now, I see 2 choices. I could move the sine squared over, take the square root of both sides, and then I would have cosine equals sine. And actually, I'm thinking that might be what you guys would do. I'm gonna go practice an identity. Because cosine squared minus sine squared, does that look familiar at all? Do you recognize that that is actually the identity of cosine 2x? Well, it is. So I'm going to change cosine squared minus sine squared to be cosine of 2x, and I'm trying to find when that equals 0. So we did some of these on that prerequisites packet. Imagine the 2x here is just your big giant theta. So forget that 2x for a second. Think about your chart. When does cosine equal 0? Well, cosine equals 0 at pi over 2 and 3 pi over 2. But since the angle was 2x, that means it's 2x that has to equal one of those numbers. And if I solve for x, that means x is either pi over 4 or 3 pi over 4. All right, so those are my critical numbers. And then remember we said what we're going to do with those is we're going to create a number line that represents the derivative and put those number on there. And notice that in this problem, they narrowed down. They told us to only use the interval from 0 to pi. That's going to happen a lot when we're talking about trig functions, right? Because of how they're periodic and they repeat themselves. So here's my derivative. I'm only going from 0 to pi because of the directions in the problem. I have a critical number at pi over 4. and 3 pi over 4. And now I'm supposed to decide if the first derivative is positive or negative. Well, remember my first derivative is actually cosine of 2x. So one way to decide, I can't do end behavior, it's not a polynomial, but one way to decide is to pick a test point and plug it in. I think what I'm going to do is, I'm going to just think through the quadrants. I do that a lot of times with trig functions. So if my angle up here is 2x, my angle is 2x, so at 0, that would be cosine of 0, right? At pi over 4, that would be cosine of pi over 2. So think about it. If my angle is 2x, then really aren't I thinking about if cosine is positive or negative between 0 and pi over 2? Well, that's just the first quadrant, and I know the cosine is positive in the first quadrant. Okay, so if I go from pi over 4 to 3 pi over 4, well, remember my angle is 2x. And so if x is 3 pi over 4 and I multiply that by 2, that would be 3 pi over 2. So the second interval means between pi over 2 and 3 pi over 2, which is the second and third quadrant. And I know cosine is negative in the second and third quadrant. And I'm sure you're already guessing this last section is going to be when 2x would fall in the fourth quadrant, and I know the cosine is positive in the fourth quadrant. Okay, if you didn't catch what I was doing with the positive or negative, just pick a test point and plug it in. Like maybe in this first interval you pick pi over 6, and then plug it in and see what you get. I just think it's easier with trig functions to think quadrants. Okay, so now we're going to label everything we need. So I'm going to say that the function, the original function, is increasing on the interval. Well, notice the derivative is positive from 0 to pi over 4, and from 3 pi over 4 to pi. And we always use parentheses when we're talking about intervals being increasing or decreasing, because we don't want to include the endpoints, because really at that endpoint it's changing from increasing to decreasing, so we don't label it as one or the other. Then I could say f is decreasing on the interval from pi over 4 to 3 pi over 4. Okay, what about relative max or min? Well, notice derivative changes positive to negative right here at pi over 4. So I'm going to say f has relative max at x equals pi over 4, because that's a specific point where you have a specific maximum. And then I could go on to say because derivative changes sign, and you have to be specific, positive to negative. And then I could say f has relative min at x equals 3 pi over 4. Derivative changes negative to positive. Okay. Now, I know this seems like a lot for one question, and it's just because we're practicing the notation and the rules, but on an AP exam, they wouldn't ask you all of this in one question. Like in one question, they might simply say, what are the critical numbers? Or in a different question, they might simply say, when is the function increasing? Or on another question, when does f have a relative max? So you're only going to be doing one part. You won't have all this writing. Okay, so how does this work on the calculator? Well, it's exactly the same. It's just that sometimes instead of us having to find the derivative by hand and find the critical numbers by hand and then determining if the derivative is positive or negative by hand, I can do all that part on the calculator. So notice number 3, we're given the derivative function, right? Not the original. And then I get to use the calculator, and they ask me to find relative max and min. Well, the reason they didn't give me the original is because you could do that on a calculator without doing calculus. Like you could just look at the graph and see where those little hills and valleys are and then give the relative max and min. But we want to practice calculus. So if I put this into my calculator, I'm going to put this in as my y1. I know I'm calling it the derivative, but I'm going to keep in mind, I'll put it in as y1. So I'm going to put in 2x squared minus 3 natural log x plus 5 minus e to the x plus 6. Now, Yes, I'm going to look at the graph, and they didn't, restrict the domain. I'm going to look at the whole graph, but remember, all I really want to analyze is what are the zeros, and does it change positive to negative? So I don't really need, I'm going to look and see what the window is right now. Maybe I'll go like a zoom 4 to start off with and see what it looks like. Hey, that looks like a pretty good graph, right? Okay. So I'm going to analyze this derivative, and I like to still kind of write it down as a number line. I just think it helps us look at it. So I need to go in and find those zeros. Hopefully you can see my cursor. So I can tell there's a zero there. It looks like it's x equals 0, but I'm going to use the calculating the zeros feature of the calculator, because what if it's like just a decimal number? And I see there's a 0 there, so it looks like there are 3 zeros, meaning 3 critical numbers. So let's go in and find the zeros. So second trace, I want to find the zeros, and I'll find this first one. So I need to move this little dude. Let's see, well, that works. So enter, move my cursor just to the right of that one, enter. So my first 0 is, I need my glasses, 0.1214. Now I know that we always use 4 decimal places, but just for the sake of having space on my number line, I'm just going to use 2 for now, okay? 0.12. So I have 0.12. Okay, I'm going to go in and find the other 2. You all can do that. You don't need me to do that. Second trace, the 0. So I'll use that for my left bound. Just go past that second one. Enter. So that one is 1.10. 1.1. I know I'm just estimating. Well, I'm not estimating. I'm cutting it off sooner than I normally do, because I'm not trying to be as exact in these notes. And then I'll find that third one. Okay, those are left bound. We'll just pass there. There's a right bound. So 2.59. So this one is 2.59. Okay, now I can look at my calculator and I can see that when I'm in this interval, until I get to that 0.12, this graph is above the x-axis, so it's positive. Then it goes below, so that interval is negative. Then it goes above, so that interval is positive, and then it's below the rest of the time. So this one goes positive and it alternates, right? So positive, negative, positive, negative. So that's the use of the calculator. It did all the work for me. But now I'm going to answer the question. If I want to talk about relative extrema, I'm going to say f has relative max at, well, look over here. The derivative changed from positive to negative at 0.12, but also at 2.59. So there are 2 relative max. That's fine. So relative max at x equals 0.12 and x equals 2.59. And I can say f has relative min at x equals, notice the derivative changes from negative to positive, at x equals 1.1. And remember, we really should go on to say because derivative changes negative to positive. I guess up here I should have said derivative changes positive to negative. Okay, so that's how you find relative max min and how you determine if a derivative is increasing or decreasing. So the homework, you can see it in my PCA, but also this, I've got it listed here. So where it says this part 1, this is in that online textbook. This is section 3.3, where it says page 186. And then part 2 is similar to the calculator example I did with you, but it's right here in this notebook page, page 70. So you're going to do 1 page in the notebook, page 70, and then these 1, 2, 3, 4, 5, and then 65 through 70. So about 10 problems from the online textbook. All right, good luck with that. I'll be back next week, and we'll answer questions. And I'll also answer questions from the previous section if you need me to. All right, good luck.